In the last video, we learned about predicates, which are like propositions, but whose truth value depends on the value of an input variable. We mentioned briefly that there's a way of turning a predicate into a proposition with a definite fixed truth value by making a secondary statement about how often the predicate is true. Let's dig into that concept some more. So here's the proposition we first saw in the last video. P of x is the statement x plus 5 equals 12, where the domain is the set of all real numbers. This again is a predicate, not a proposition. This statement is neither true nor false as it is, because it has an undetermined variable in it. But let's form a new statement that's related to it. The statement P of x is true for all values of x. Now this statement is definitely false, because we know for a fact that P of x is not always true. That is, we know that x plus 5 is not always equal to 12. In fact, P of x is only true for one and only one value of x, namely x equals 7. So the statement P of x is true for all values of x is definitely knowably false. That makes it a proposition, not a predicate. Here's another secondary statement we can make from the original predicate. P of x is true for at least one value of x. Another way to say this is that P of x is sometimes true. Now that statement is definitely true because there is at least one value of x that makes P of x true, and we even know what it is. It's x equals 7. So again, predicates by themselves don't have enough information to know whether they are true or false. We sometimes say that they are underdetermined because the variable prevents us from knowing the truth value. But when we make a secondary statement about how often the predicate is true, for example, this predicate is always true, or that predicate is sometimes true, these statements are propositions with truth values. We call this process quantifying the predicate. To approach computer science from a mathematical point of view, we often have to make claims about patterns we see or algorithms we create and then give an explanation. Those claims often come in the form of quantified predicates. For example, in an earlier video, we saw an algorithm that converts a base 10 integer into base 2. We did not, however, discuss whether this algorithm always works. Doing so would involve working with a quantified predicate. The predicate would say, this algorithm applied to the integer n produces the correct binary representation. And what we want to know and explain is whether P of n is always true. So this notion of quantifying a predicate is really at the heart of computer science in important ways. As we saw a moment ago, there's two ways to quantify a predicate. One way, like in our example with the algorithm, is to claim that the predicate is always true. When we take a predicate P of x and make the claim that P of x is always true, this is called universal quantification. We have a special symbol for this that looks like an upside down A, which you can remember because this means for all x, P of x is true. For example, if P of x is the predicate x plus 5 equals 12, then for all x, P of x is the statement that x plus 5 equals 12 for all real numbers x, which, as we saw, is a false statement. Here are some more examples. Let q of x be the predicate x squared is bigger than or equal to 0. For all x, q of x is the claim that x squared is bigger than or equal to 0 for every real number x. And that's actually true this time because we know from basic math that squaring a number always produces a result that's bigger than or equal to 0. Here are two more. R of x is the predicate the length of x is positive, where x is a string, and S of x is the predicate the absolute value of x is negative, where x is a real number. Pause the video and find the truth value of for all x R of x and for all x S of x. So in these examples, both universally quantified statements are false. It's not the case for every string x, the length of x is positive, because there is such a thing as a string of length 0, namely the empty string. So for all x R of x is false because we found what's called a counterexample, a single example that shows us that R of x is sometimes false, therefore not always true. Likewise, for all x, S of x is false because there's a counterexample there as well. In fact, there are many. For example, x equals 1. The absolute value of 1 is just 1, which is not negative, so S of x is not always true. The other form of quantification we have is when we take a predicate and claim that it is sometimes, but not necessarily always, true. For example, if p of x is x plus 5 equals 12, then while this predicate is not always true, it is true for at least one value of x. A fancier way of saying this is that there exists an x that makes p of x true. This form of quantification, where we make a claim about the existence of at least one value that makes the predicate true, is called existential quantification. We use a special symbol for this too, a backwards e. So this notation means there exists at least one x such that p of x is true. We saw that there does exist an x such that x plus 5 equals 12. So the statement, there exists an x such that x plus 5 equals 12, is a true statement. Remember that the universally quantified version of that predicate was false. If q of x is x squared is bigger than or equal to 0, then since this predicate is true for all x, it's certainly true for at least one x. Now you try it with the earlier predicates r of x and s of x. Are the existentially quantified versions of those predicates true, or are they false? There does exist an x such that r of x is true this time, because it is true that there exists at least one string that has a positive length. For example, the word logic has a positive length. But the statement, there exists x such that s of x, is false, because there does not exist even one real number whose absolute value is negative. Here's a table that summarizes what we found in these examples. So in this video, you learned that taking a predicate and quantifying the variable turns it into a proposition with a truth value. And there are two ways to do this, universal or existential, each of which has its own notation. You also learned that a counterexample can be used to prove that a universally quantified statement is false. The next video is going to look a little more at this idea of proving quantified statements are false by asking how do we negate a quantified statement.